So last time we have seen how to use the algebraic type system to write concise and reusable components. We used the option type and we used higher order functions to get rid of duplicated code. And we have looked at the definition of product types, tuples, records. So what we can basically do is we can combine the product types and the union types, or the discriminated unions, as we call them in many languages, to do something more useful. Just quickly wanted to note what's the type system and what are we using here. Until now, we have used the algebraic type system. The type system is actually more than just that. In what is a type system? Every term has a type, for example in Java at compile time, and for example in JavaScript at runtime. However, the type system is still there, so it's useful to talk about types also when we're talking about JavaScript. Type systems may support object-oriented programming or generic programming. Haskell or C++, for example, are strong in generic programming. In OCaml and F#, for example, we have the algebraic type system as a basis, and then they added object and object-oriented programming support on top of it. So this is kind of a similar approach, but from the other direction. In C#, they started off with an object-oriented type system, and then now they are just adding algebraic type system components. So let's do something useful. Let's define a type called private customer. What is it? The private customer has a name and an ID. Then we have a corporate customer, which also has an ID, but also has a name of the company and the Umsatzsteuer ID. Now we create a customer which is either a private customer or a corporate customer, and again what we can use here is, of course, since we have two types of customers, we can distinguish between those two by using a discriminated union. And the data behind of the discriminated union can be modeled simply as a product type, in this case a record. However, in F# you can also mix those two and inline, so to speak, the definition of the product type into the definition of the union type, which results in this definition. What can we do with this? By using, for example, the list construct, we can create a list of customers by having first the private customer and then the corporate customer. How we do domain modeling and domain logic by using algebraic type system, we'll see in a few lectures. For now, let's more think about the last line here. What have we used here? We have used a list here, and we have created, it looks like a heterogeneous list. Actually, it's just a list of customers whereby each component is either a private or a corporate customer. But what's this list construct here? Actually, lists are built in F#, but we can really just write a list from scratch on our own. And let's see where we get. What's the simplest list we can think of? The simplest list is just a linked list where we have single linked list nodes, where we have the first node here, which has as a payload 0. Then we have the second node, which has 1, and then we have the third 2, and then we have a pointer to null. This is like we do it in algorithms and data structures. So when we think about this in a structured way, a node has the data as a payload and either points to the remainder of the list or to 0. And this is exactly the definition of the algebraic type system when we use discriminated unions. So please let's look at this definition here. We have here the linked list of A. pretty similar as we had it in option. We have a node which is composed of a value, the payload, and the rest of the list, or it's null. And how can we create a list? We can create a list by simply using the constructors of the discriminated union in order to create a list as such. What we typically have, they have special names. So the list is typically structured as such. A list of A is, the first constructor is called cons for construction of the list, which takes a value, the payload, and the rest of the list, or nil, which corresponds to the end of the list. So this is actually the definition of a list, 1, 2, 3, and then the last one is nil. Single linked lists are so important in many languages that they often have a special operator for those constructors. The first one is the empty list, which corresponds to nil. So we can use this empty list here instead of using the constructor nil. Also, cons is often referred to as those double points. In F# we have double point. In Haskell, for example, we have one single double point to refer to the constructor cons. As we can see here, when we look at the structure, typically when creating a list, we talk about creating the remainder of the list, and then we add something in front. So actually this imposes the order of the operations. However, the cons operator is typically right associative by default, which means that we can simply write it as such by neglecting the parentheses. However, since this is still not really comfortable, functional languages often have special support for string literals. So here, this L5 actually corresponds to the definition as such. What can we do with lists? Actually, let's define a list. Here we have L5, which is 1 and 2. So L5 is here, and it points to this node where we have 1. Then there comes the tail. The remainder of the list is often called tail, which refers to the second node, to 2. And here is a missing node. Actually, here it should go out to nil. And then we create the list L6 by consing, as we often call it, by calling cons on the L5, which means that now we create L6, which is a new list whereby the first component of this new list is the 0. We just const to the list, and then it points to the previously existing list L5, as we can see here. When we write it with the operator, we can define L7, which is 0, double point, which is just the call to list cons. And we here create a new one. So here L7 is just a pointer to the, or here is a mistake, we need to fix it. Maybe it's not too bad. We have here this function here, this value here, L7, which points to 0, and then it points to the other, to the remainder of the list. And we can also fix the other mistake as well. Actually here it goes to another node type. Let's say we have here the nil node type. Now everything should be fixed and we are ready. What can we do with this with these lists? Basically, what you can do here is, let's create a list. This list is again just 1, 2, and the nil constructor added to the list at the end. What can we do with those lists? Let's now write a function which just computes the sum of the list. what can we do? Let's create a function sum, which takes in access, which is a list of, let's say, integers, and we want to create the sum of them, which is again an integer. What can we do with a list? A list is, what did we always do with option? The only thing you can do with an option is you can do a deconstruction, which means you can do pattern matching on the cases of the list. What are the cases of the list? Well, they are cons and nil. I just write it again. My list of A to see it again. So here we have my cons. I just prefix this with my, otherwise it will collide with the base library implementation. So we have A and we have the remainder of the list. And then we have my cons. This is denoted as the empty list. And this is denoted as double point. So when we do pattern matching on it, we could either do it like this. We match on the real list cons now. It's defined in the list module. We get X. This is the payload of our list and the rest. How do we compute the sum if we get a list node? Here, for constructing the sum, we of course need to take the payload and we need to add the rest of the list, the sum of the rest of the list. So we need to create here sum call onto the rest of the list, like I said. And then we have the second one. It's in the base library, it's even called empty, not nil. However, what's the sum of an empty list? It's 0. Instead of having those, we can also use the operators. And instead of rest, we often use the term access for many variables of type X. In that case, it's the remainder of the list. So here we have this. And for pattern matching, we can use the empty constructor. It's really just the constructor actually, and we have 0. Then we are left with this error. Sum is not defined. Why is it like this? Here we are in the sum function, and everything in F# which is defined at the position is only available after its definition. Here we are in the definition of sum, so sum is not available. For that reason, we need to define this function to be recursive so that sum is available within the definition of sum itself. What can we do with it? Now we can compute the sum of the list, which is 7. We can also, let's say, we would like to write a function which filters out elements of a list depending on a particular predicate we give it. I mean, let's say we let's write it non-generically first. Filter once. So we want to write a function of x which takes a function. We don't need to write the types here actually. When we have an element, and if this element is 0, then we skip it and filter once in the rest of the list. Otherwise, if it's non-zero, we take it by again doing the constructor of cons here and call filter once, cons it to filter once of the rest. I'll just write it a bit easier to read like this. We have here the case when we want to drop it, then we drop it, otherwise we keep it. Again, it needs to be recursive. And what happens when we have 0 elements in our list? We cannot filter out something. So let's try it out. So now, it's called actually filter out once. So let's filter out once. So 1, this will be skipped, 2 will be here, 4 will be here, and 1 will be skipped. Okay, 1 is gone. What if we want to write this generically? Let's say we want to define the function filter. It will be recursive, I know it now, because it will be defined totally analogously to the filter ones. We take in, we call it filter, we take in the list, and we take in a predicate. Let's write the types, because then it might be much clearer. So we get in the list of A, and we get in a predicate which maps from A to Boolean, and then we return a list of A's. So here now we perform pattern matching on the list. When it's empty, well, then it's empty and we don't need to filter. When we have an element and the rest, we need to ask ourselves the question, is F, should we take X? F is the oracle or the machinery which tells us, should we take F? So we say, okay, if F of X, then take it, which means that we take it, so we leave it in the list and create it, give it into the new list we return. So we have X, and we still need to filter the rest of the list for the predicate. So we call filter on the rest of the list, and we apply it with the function. Otherwise, we drop it. No, if we filter it, it's okay. Otherwise, we drop it, and we just continue with the rest of the list. Now we have defined filter. What we can do now is we can write a function, or we can write an example where we say, okay, we have a list, and we pipe it this time through filter. And here the filter predicate is a lambda where we have x, and x modulo 2 is 0. As you can see now, I've just made a mistake. The first argument here is the function. Let's write it without the pipe, then it gets clearer. It's always good when I make mistakes. So here we get an error because filter takes first the list and then the function. And as you have seen now, it disallows us from piping it in a really awesome way. So let's switch off the arguments in the function here, and let's first have the f and then the x's. Great. Now it works. We can filter this list by applying this predicate. And bloop now is 2 and 4. We only have the non-outsider, are they called, the modulo 2 is 0 values in our list. And what we can do now is we can rewrite it in such a way that it's a piping. And what can we do here again? Of course, we can do much better stuff. We can already pipe it into sum, and this is actually part of the exercise we did in a previous lecture. And what we can see here now is we did the sum on all non-odd numbers we just applied to the function. And this is really, again, now we have really implemented the internals of such a list. Previously we used link, now we used our list type. We didn't use our own list type now, but it's really the same as the built-in list type, and we arrive with a very simple definition and really composable operators to work with lists. Let's see if we still have something. Or here we have another example where we say, okay, all elements smaller than 10. So what have we done in respect to the last lectures? We tried to write more robust code by talking about non-existence of by talking about the non-existence of values by using the option type. This was done by using types. Then we used functions and higher order functions to write small testable parts which can be chained together by using piping or by using function composition to write bigger programs. And finally, we even implemented a list type. So what have we learned so far? There's an algebraic type system. We have learned about the list type and the option type, and we have developed simple composable operations on lists. What's up next? What's about lazy evaluation we have talked about when we were talking about links? Link. What is this really the precise semantic of functional languages? How do they work? How do they run on a normal PC? What can we do more with algebraic types? What about modeling domain logics and describing domains by using algebraic types? This is really a great one, and we'll see this in a few lectures. Also, we will talk about testing programs and how to integrate functional programs in real-world applications so that they integrate and each paradigm benefits from the other one. So this was the end of this lecture, and we'll see each other next time.